Okay. Let's start. Nice to see all of you again. Two quick messages. One, I don't know if you know that, but in our last meeting, so this is mostly, I'm saying this for those who watch the recordings. So in the last meeting, I didn't share the screen to Zoom, and then the recording didn't have the slides, and Shai tried to fix something that wasn't great. And so what I did, I re-recorded it from home. So there is another version of the recording of our last meeting. And also I added there this TensorFlow demo thing, like a tiny neural network with some observations. So you can watch it. And the second message is that homework 1 is due today, and homework 2 should be out today. I don't know if it's already out or... It's already out. Great. Okay. So let's move on to today's topic. So we've already been familiarized with neural networks and backpropagation, but what we were familiarized with was what we call vanilla neural network, fully connected neural network, MLP, multi-layer perceptron. You choose whatever name you're convenient with. And today we're going to learn about this other type of layers, other type of neural network, which is a super common type and very important type, and maybe the one that created the deep learning explosion. And it dates back to the origins are in 1979, Fukushima, and then Jan LeCun took the structure and added backpropagation to it. And the convolutional neural networks, CNN for short, are a huge revolution and probably one of the most important types of neural networks, and what made the revolution happen. So we'll start by recognizing what we expect from visual recognition systems. So this is where we get computer vision into this learning lessons that we had. And we'll understand what a conv layer is with all other terms, and then we'll take it to 2D. This is an important step. We want images are two-dimensional, and we work with them. And we'll learn some more things. Then we'll talk about how it's being implemented and how it's being trained. How do you do backpropagation through this? And we'll have some intuitions about what is encoded in these things we call feature maps, and some other elements that you usually see when you deal with the neural networks. All right. So I want to start by motivation. When us humans look at this, I want to make sure we're recording. Yes, we are. And Zoom people can hear me well? Just a thumbs up or something, if you can. Yes. Okay. So, us humans looking at this picture, we know this is somebody's desk. And it's an interesting question to ask, how come? How do we know that this is somebody's desk? And one way to look at it is to start by saying, okay, you can look at something very, very small. This is a horizontal, this is a vertical line that I see here. Recognizing a vertical line is very easy. You don't have to do machine learning for it, right? You can have some kind of filter, look for it. Anybody can come up with non-learning based code to recognize a vertical line. And there is another vertical line here. And then there are these two horizontal lines. And if you recognize these, together with some maybe more delicate features like this, and you can have some system that would know that this is probably a key. Okay? Are you with me by now? Then in the same way, you can recognize more of these keys. And after you do that, you can come up with the conclusion that this is a keyboard. And the same way, you can probably know that this is a monitor and this is a mouse. And then you take all of this together. You concatenate this knowledge together, and you know that this is a desk. So I want you to notice what was the process that we just did. What happened? we started by recognizing things that don't require any learning, that can be recognized with non-learnable system, some one silly filter. But then, when we concatenated information from several of those, we could use some kind of other system. This would require some learning, probably, and know that these bunch of lines together make a key. And these keys together, and then once we named it, we said, okay, so this is a key. Now I know this is a key. Now let's go up one level. And whenever I see lots of these keys, and what is a key is this thing that I recognize with those lines, now I know it's a keyboard. So two things are happening at the same time. As we go these sort of levels up, two things are growing. One is our field of view. We started by looking very narrowly at these very small lines here, and it all grew. We ended up with the entire image. So the field of view was growing. The second thing that was happening is the complexity, because the perceptual level of the terms that we use. Because a vertical line, I believe everyone in this room can write simple code to check whether or not some image is a vertical line or not. Okay? But I don't think any of us know how to write our own code, not a learnable algorithm, our own code that recognizes a key. And maybe you can. It will be pretty hard, I guess. I'm sure you cannot do code that recognizes a keyboard and of course not a desk. So the complexity, the perceptual level of the terms that we're using keeps growing as the field of view keeps growing. Okay, so these are the two important observations about this approach of understanding visual recognition. And here's another thing that I want to notice. So this is a monitor, fine. Now, let's say I move this image like this. What do you think should happen to this bounding box that indicates where the monitor is? It's a very easy question. It should move along with the image, right? Right? So this is also something that we should notice. This is called equivariance or shift equivariance. This means that if something moves, it doesn't mean it is changed in the sense of the perceptual understanding of it. It's not the same, okay, because it's shifted, but our recognition of it is also shifted. Okay, we'll give better terms to these things. Just like, you're with me, you understand what the point I'm making here? Because it's not trivial. It's not trivial because think about this. This image is what? Is a list of numbers, a list of pixels. And for example, what you're about to do in the homework, in like homework number 2, I believe you'll be working with this MNIST data set at some point. And then you'll take such images and you say, okay, what can I do? Because the networks that we're aware of today, they operate on these vectors. So I can vectorize this. I'll take the pixels like one by one, like this, 1, 2, 3, 4, then the second row, then the third row, and I will have a huge, very long vector, and I'll operate over it. Now think about this vector and these weights. What's happening when I shift this image? It's pretty hard to kind of, so all the values in the tensor change, and there is vertical and horizontal, and you feel me? You know what I'm saying? So this is not a trivial thing when coming to think about it, this invariance that I'm showing here. So let's try together to go through all these expectations that we have of a visual recognition network. So the first thing is just what I was talking about now, is you want to maintain the 2D structure logic. Okay? In the homework you're going to do now, where you're going to ruin this 2D structure and make this one long vector, you lose a lot. You don't understand if there was one pixel above another. they're going to be in separate places in this vector, you lose this sort of relation, okay? So we want to keep holding this 2D thing. This shift invariance we just saw, and we want to consider local correlations first. So we looked at this horizontal line and vertical line, they were next to each other. It wouldn't help a lot if I say that at this point in the image there is a vertical line, and over there is a horizontal line. I can't really do something useful knowing this. So I start with the local correlations and then I gradually grow. So this is where comes hierarchically growing field of view that we talked about, and hierarchically progressing complexity, which we also just mentioned. And then we want a reasonable amount of parameters, okay? So to understand why I'm pointing to these things, we'll first go to what we already know, which is the fully connected layer, okay? And this is how it looks like. And you can see then we have, in this case, just one layer and eight input neurons and 8 output for these layers. And you can characterize this network by this layer, by a matrix. And how many weights does this layer have? 8 squared. Sorry? 8 squared. 8 squared, yeah, 64. So help me out here. Let's go through the list and see what does the fully connected layer maintain, okay? So does it maintain 2D structure logic? No. Okay. Is it shift invariant? What happens if I sort of, I don't know, if I shift everything by 3 pixels? Will the output also be shifted? No. It's going to be multiplied by other weights, right? What used to be here that is now there, for example, this was multiplied by these values, which are different values from here. So you're going to get a whole other thing, not related at all. So there is no equivariance in the shift. Okay. Does it consider only local correlations? No, it's all fully connected, as its name. Does it have a hierarchically, say I have many of those layers? Does it have hierarchically growing field of view? No, because it has all the correlations to begin with. Does it have hierarchically progressing complexity? Anyone?
No.
So this is the one thing that it does have, right? And you can look at this demo, or try it yourself. This MLP demo. There's a link in the previous class. So for example, if you only have this is linear. Now you add this nonlinear activation and another layer, it becomes more complex. And the more layers you add, this is the one thing that does happen. This is representation learning, and each layer you have, you get a representation that is more complex and eventually can have a semantic meaning. And I want to say about the amount of parameters that no, this is not a reasonable amount of parameters, because think about an image. Say you have, so let's take an average image, which is 1,000 pixels by 1,000 pixels RGB. Okay, so we're talking about 3 million values. You're with me? Good. 1,000 by 1,000 by 3. And let's say I have a fully connected layer. I have this as an input, and I want output the same size. So I'll have 3 million in the input, 3 million in the output, and which means that just for this one layer, I will need 9 trillion parameters. Okay, that's almost 10 to the 13 parameters for just one layer. Yeah.
Isn't in a sense number 6 the only real impediment that we have? Like I feel like 1 to 4 we can all put it into by choosing the appropriate values for the weights.
Yes. Yes.
Number 6 is the only one that is really prohibited.
Well, I mean, the short answer is yes, but not exactly. We can discuss this, but I see where you're coming from, and we'll actually even emphasize this in 1 second. Can you raise hands in this crowd, who knows what a convolution is? Okay, most do. And if you don't, it's fine too. I mean, it's not fine. I mean, you should all know about convolutions because it's a very important thing in science altogether. But you can learn about convolutional neural networks without knowing what a convolution is. It's technically possible. Okay? Since most of you are aware of what a convolution is, I'll just highlight the fact that, so it has this integral expression, and those who are not familiar with can see it as a bit of a scary. But eventually, convolution sort of takes two functions. So it's a functional. It gets two functions, and sorry, it's not a functional. It gets two functions and returns a function, and it sort of takes this correlation. So there is the shift between those functions, and for every value of that shift, it returns a value that says how similar these two functions are in that shift. So you can see that if I take those two window-looking functions, the highest it gets is 0 because they're both centered. So when there is no shift at all, this is the highest. And when they're very far away to the extent that they don't overlap at all, these two windows, then you get the 0 value. So it sort of does this. I don't have the capacity now to teach all the math of the convolution. Those who are not familiarized with this, I encourage you to read about it. There's amazingly important meanings in all kinds of fields. And we're going to talk about this thing that is called a convolution layer, okay? And this is based on a discrete convolution, which I assume most of you know, but if not, it's not critical for this. Any question here? Okay. So we used to have this fully connected layer. We're going to have a different rule now, okay? So stay with me. We have this color coding. You see this A, B, C. So whatever the weight is A, going to be black and so on. And I look at the output, x0, x sub 0, and it's going to be the sum of just three things, okay? So it's going to be the input x0 multiplied by A, x1 multiplied by B, and x2 multiplied by C. In this example, we say that the kernel size or the filter size of this convolution is 3, okay? Because we have those 3 weights. And then x sub 0, the output, is the sum of only, it's like the linear combination of only 3 neurons. And these happen to be the neurons that positionally match these output neurons. So far, so good? Okay, then when we look at the next one, it's also positionally taking those that are, let's call it, in front of it, okay, using the same weight, the same A, B, and C. Okay, so and I think you understand what's going to happen next. So you understand that the picture here, there are 2 things that are different that we need to pay attention to. One is not every output neuron sees all the input neurons. It only sees part of them. This is one thing. The second thing, even after this, other neurons that see other input neurons, they're using the exact same weights. Okay? We're okay? We understand the structure? This is how it's going to be. When I'm done doing all this thing, I will add the bias term to each neuron, just as you do in well, not exactly. Yeah, okay. I'll say something about the bias later. It's actually not accurate the way it's written here. You do add the bias term. Now, try to help me out here. I want to formalize this as a matrix, this specific example as a matrix multiplication. Okay? So the output vector equals this matrix multiplied by the input vector. And what do you think is going to be right here at the top left? Sorry?
ABC.
A. Okay. You're going fast. I'll start just with A. Okay. So, right, this A is because of this top black line that you see there, black arrow that you see there. Okay. So x sub 0 equals A x0 plus B x1 plus C x2. So this is going to be now B. And what's going to be the rest here? Just this first line. C, and what after C? All zeros, right? Because all the others, there are no weights there. But as was commented by you, sorry, what's your name? Gali. So as was commented, you can think about it like there are arrows here, but their value is 0. Okay? So, who's going to tell me what's going to be in the second line? 0, ABC, right, and so on. And anyone knows what is if the term for such matrices? Sorry? This is called Toplitz's matrix. You heard this term? This is called a Toplitz. Actually, it's a special case of a Toplitz matrix. And this is how it looks like. And now we understand that that you can look at a convolutional layer as a special case of a linear layer. This is a good thing because it means a lot of the tools that we had for thinking and working with those regular linear layers are still valid. Here is a healthier way to look at things. And so instead of thinking of this list of weights, I'm not saying that this is what's happening behind the scenes. I'm saying that a way to think about it is you have this filter, and this filter is traveling over the input, okay? And every time it produces this, it just produces this output. So we have these 3 weights. We take the sum, and we get x0. And then if you were to implement a convolutional layer using a for loop, which you will never ever do, and don't even try it, okay? But if you did with the for loop, then this is how probably you would do it. You have this filter, and then you go each time go 1 step, multiply by what it sees at this moment, and then you get all those inputs. Okay. Here's a question. Let's say we have the input size n, and the filter size is k. So in this example, it's 8 and 3. Okay. So let's say we have n and k. What is going to be the output size? Yeah, but I'm asking for n and k. General. Almost.
+1.
Yeah. So okay, that's a very machine learning way of getting the result. What you do there? Okay. So the answer, yeah, is n minus k plus 1. Why? Check for yourself. It's boring. Okay. The next question I have, is this a pure convolution? Is what I'm seeing here a discrete convolution between this input and the vector a, b, c?
No,
Why not?
it's none of them is shifted. It's cross-correlated.
Yeah. Okay. I think I know what you mean, and that this is the right answer. So in convolution, you have this minus thing. And here it's exactly what it says, cross correlation. So it is a convolution, but it's not a convolution with ABC, it's a convolution with CBA. Okay, so it's cross correlation with this filter. Okay? Or you can always say it's convolution with this flipped filter. Okay? All right, moving on. So there is this thing called stride, and stride is our way of getting an output vector that is smaller than this predetermined size, okay? And it's very simple. What we're going to do is, if you think about this traveling filter again, instead of moving one step, the filter is going to jump, okay? So in this case, it's going to jump 2 steps each time. So we'll get less outputs, okay? So here is one jump, then another jump, and then you get an output that is smaller in size than the input. Okay? Let's think about this matrix again. This is what we had before. Okay? Trying to understand what's happening now. And the thing is, if we didn't have the stride, this was the matrix that we would use. And the only thing we did, we could have done it, and then we had those outputs here, but we just threw them away. We're just not interested in them. So thinking about the matrix, this simply means we just kill those rows out of the matrix. And this is how it looks like now. So it's not a square matrix, and so it wasn't square also before. Okay? But we get this type of a matrix. Here's another, maybe a little harder question. Say we have input size n, and we have the filter size k, and the stride is s. What's going to be the output size? Any quick thinkers?
Minus k plus 1 minus s. No, minus.
Wait.
N divided by k plus n mod k.
Again?
N divided by k
Okay.
plus n mod k, something like that.
Okay. Yeah, it's boring. Yeah. So it turns out it's n minus k divided by s plus 1. Try it. And if you look at PyTorch documentation, there's also other things called dilation and whatever, and then this becomes like a very big, boring formula. And okay. Next thing is padding. Okay, we were just going through like basic tools that we need for us to use convolution. So we saw that for example, when we have the same size of when we have the no stride, we get the input a tiny bit smaller, right? Sometimes we don't want it to be this way, and sometimes we want to be able to control the output exactly. So you would want, for example, maybe for stride 1, so means no stride, to get the exact same size, and for stride 2, maybe to get exactly half of the size, things like this. And basically, before we didn't have this x0 position, right? And what you would want is to just, okay, fine, I don't know what other weights to use, so I'll just use these 2 weights, the red and the green weight, and the black weight will be missing. And a metaphoric way of looking at it, thinking about this traveling filter thing, is kind of, it gets stuck. Okay, so this filter is like this, I don't know, car or whatever going here, and then it gets stuck in the end here, so it can produce this. Okay, this is just my imagination of things. So if it's stuck, what we can do is we can add one more neuron there. So if we don't want to get a smaller output, we'll just do this padding. So we add more neurons. The classic thing is 0 padding, but there are other policies. You can take the neuron that was on the boundary and use it again, and other stuff like this. And now we get what we wanted, because 0 is multiplying this black weight, and now we have only the red and green. So we get this padding thing. Okay. And now we get all of these. All right. So far, so yeah.
To handle the half the filter, to put it in the same size as the input.
Sorry. So what's the question?
The motivation to the padding.
Yeah.
Let's say that your filter in the convolution 3x3, so you will do a padding of 1 because it's half the filter.
Yeah, you can do other padding as well. You can have other motivations, but one good example is when you want it the same size.
Yeah, you
So-
want, eventually you want the same.
Yeah, so if the filter was size 5, I would add 2. Okay. Now I'm not going to ask. Now you can add. Remember this formula of the size of the output. You now add padding to the formula. I'm not going to ask this. Okay.
Why would you want it the same size?
Why would I want? There can be many reasons. So what if my input is an image and the output should be, okay, my input is a noisy image and my output is a clean image. I want to be the clean image. So I want to be the same size. Okay? Okay. But it's not the only thing. I mean, sometimes I just want some specific size and the padding helps me, doesn't have to be the same size. Now let's move on to one of the biggest motivations for it, which is a 2D convolution. And even though it's called 2D, we're going to move from one-dimensional vector, not order 1 tensor, which is a vector. We're going to have order 4 now, okay? And this is the structure everybody works with. So let's go through how this thing is built. We can look at an image, as I mentioned before, as this 2D array of pixels, but each pixel also has channels. So in this particular example, you can think of an RGB image, but there can be many channels. It can be thousands of channels if you want, okay? So we're seeing, what we're seeing now is an order 3 tensor, like an array of order 3. But there is actually one more order to add, which is, remember, we always work in batches. So what you see here, think about, I have many of these, and altogether, I call this a 4th order tensor. Okay? N is the batch size, C for channels, height and width. Okay? The only thing you're not seeing in the illustration is that there are N of these. So far, so good? We're okay?
N is the number of batches or the size of each batch?
No, the size of the batch. Okay. All right. Now, when I want to do convolution to this thing, I'm going to use this filter, which for now, you can look at it as a order 3 tensor. Okay? And you can see, and I'm going to put it on the image in a second. So it has C, and these are lowercase h and w. It's like the size of the filter. So we used to have a filter size 3. Now there are like 2 sizes, 2 special sizes. So this is a 3x3 filter. Okay? This C is a capital C. It's the same C as here, and it has to be. Okay? So my design choice here is H and W, but not this C. This has to match. Okay, this is still the design choice of the previous layers or something, okay? But for this filter, it has to be.
So there's no reason to say that some channels are more correlated than others. Or
There could be, but let's get to there, okay? Okay, so this is how it's going to work. You see, I sort of put the filter over the image, and just this metaphor way of looking at this traveling filter we had before, we have this traveling filter now. And what it does, all those neurons that it touches, all these values that it sees now, there is 3x3 in this example, 27. It has a weight. It has 27 weights. It multiplies each of these 27 values, it sums them all, and we get this one result here, one value. Okay? We're good? Then you do this traveling thing. So you move. Okay, it doesn't, you can imagine that it moves in rows and then in columns, whatever you want to imagine. Okay? But it keeps moving, and each time it produces one more value. Okay, and this is how we get our output from this convolutional layer. The output size is going to be N, same batch size. Okay, for each instance in the batch, you're going to get this. Only one channel, okay, because it took all the channels together and produced one channel. And then this H tilde and W tilde, it depends on the stride and on the padding and whatever the calculation we talked about before, this N minus K divided by the stride plus 1. Okay? Are we good? Here's my next question. Something is bothering me, and this is that wherever I have a convolutional layer, this means the output will only have one channel. And then when I have the next layers, it will, what am I bound to have only the first convolution in my network to have many channels, and then I'm going to have one channel all the time? No. Any tricks, any ideas? What can I do to have more channels in the output?
More kernels.
More kernels, more filters like this. So we had the green filter, so we can simply have more of these, okay? And then we will have this red filter, which will produce another channel, and we can have, I don't know, 256 of these filters, and then I will have 256 output channels here. Which brings us to rethink about the filter and all the sizes. So instead of saying I have many of those filters, all the filters together can be viewed also as an order for tensor. Okay? And this C out here is a design choice of this layer that determines how many channels I'm going to have in the output. C in has to be the same as the number of channels that I have in the input. Lowercase h and w are the spatial size of the filter, and these are also a design choice. Okay? And these are the sizes. And so you start with n c in hw, and you end up with n c out and hw that are determined by the strides and the padding and the whatever you use there. Okay? Is this clear? This is like the base to the basic convolution and how the architecture works.
So for every layer, the size of all the kernels is the same. Right? Same.
For every layer?
Okay.
No,
let's say
no.
Okay, the size of this filter kernel must be same. Same.
The same as what?
Same as the channel.
Oh, between those.
Yes.
Yeah, they have to be. Yeah. Otherwise, the output wouldn't be a tensor, right? If I have.
Yes.
Okay.
It's something patterns or something.
Yeah, you can split to two different layers or whatever, but if for a single layer, the way we define it, yes, this is a tensor, and it says those have to be the same size. Yeah.
Can we do a convolution to each channel separately? Like,
Yes, but it's a thing.
Yeah.
Everything exists. Every such question you
no,
probably
it's,
ask. Yeah.
you can, like, if you just make the other two zeros, then it will just
Yeah.
operate on this.
Yeah, there's like depth-wise convolution, and everything exists. Yeah, I'm showing the most basic thing. All right. Let's get familiarized with a term called the receptive field. Okay, so we're going back to 1D to understand this, then go back again to 2D. Okay, check out this neuron here. And very easy question. We have the filter size is 3. And look, this is layer number 2. My question is, how many neurons in layer number 1 are going to influence on the value that this neuron is going to have? I knew it. You went one step too far. I asked about layer number 1. 3. Okay, now I'm going to ask a hard question, and I'm sure nobody is going to know the answer. How many neurons? Okay, let's. Okay. How many neurons in layer 0 in the input layer are going to influence this neuron? So the answer is, if I look at all the neurons that I know that influence this, and I look at who influences them, then I get this result, which is 5, right? And what if I look at some neuron here? How many neurons in the input are going to influence this value? 7. So there is this calculation that you can do. Think about it. It's again one of those boring +1 -1 things. Okay, and if there is stride, you multiply by stride. You can do these games. My point is not how to calculate this. My point is that it exists. Okay? So you can always think about it, that some value is only influenced by this thing we call the receptive field. Okay? The deeper you go, the receptive field grows. All right? Good by now? Okay. Let's look at this in 2D. So if we have some layer, it sees some of the image, but in 2D, it's actually like this, growing window. Okay? This field of view keeps growing. The deeper we go in the network, I see more. I have a bigger receptive field. Everything is okay? Understood? Great. So, my point here is that convnets are cool. Okay? Let's check all these characteristics that we expected out of a visual recognition system. Okay. Does it maintain 2D structure logic? Yes. And is it shift equivariant? It is, right? The filter moves, it doesn't care, right? It's the same weights. I move everything, it is the same thing. Excluding boundaries, okay? But don't be like this. Okay. Okay. Does this consider local correlations first?
Yes.
It does. And we just saw that it has this hierarchically growing field of view, right? This receptive field. And that's not a new thing. We mentioned it also exists in MLP. The more layers you add, the function becomes more complex. You add this non-linearity, this activation each time. Okay? You get more and more complex, more and more semantic meaning. Okay. And finally, we do have a reasonable amount of parameters. Okay? Think about the 1D example. We had like it first, and we calculated together that for an image of, okay, let's go to 2D, sorry. I have an image, 1000 by 1000 by 3, and outputs 1000 by 1000 by 3. If I want to do this fully connected, I'm going to need something like 10 to the 13 weights for one layer. How many weights do I need for if I do this in a convolutional way with a 3 by 3 spatial kernel? Any ideas? We had 10 to the 13 before, and the answer now is 27. Okay, it's just because the same filter travels everywhere, 3 by 3, and I'm saying, maybe not 27. Sorry,
Multiple by that.
by 3, like 3 times 27, 81. Okay, it's 81 actually. Right? It's 3 by 3 by 3 by 3 because I have C out is 3. C in is 3, H is 3, W is 3, 81, and so I'm not saying it's the same thing. The fully connected is more expressive, whatever, okay? But thinking about the weights, okay, it's unbelievably more efficient.
What happened to the offset? It's not 4. There is always the B.
Oh, the bias, yeah. So this is why I had something inaccurate in one of the previous slides. So the bias goes along with the filter. So there is one more parameter.
Yeah,
so it's 82.
One of the multiplication is 4. It's not 3.
What do you mean 4?
No,
it's not. No, the bias you just add it. So there's one more value after you sum it all up. Yeah. So it's not 81 parameters. It's 82. Okay. Now here.
For one filter.
So this is.
For one filter.
Yeah. Okay. Fair enough. Yeah. It's not 82. Yeah. It's 81, and we said we have 3. So it's 84. Okay. Okay. And here are some very important observations. Now this whole convolutional world is inspired by neuroscience, like Fukushima's neocognitron, like the first model of sort of convolutional network, was for neuroscience. And I want to look at these two. Okay, let's do a quick break, 10 minutes exactly. Okay, so 10 after 10, starting again. Okay. Okay. Okay, everyone's here? Almost. All right, so I want to start with the after we know about the convolutional layer. I want us to stop and think for a minute here about the consequence. So the output that we get is not the output that we're used to. Okay, the input is not what we use as well, but we apply some convolutional layer on some input. It doesn't matter if it's inside the network on some features or the first one on some image, and you get this tensor, okay, which has this size, you know, the height, width, channels, and batch, okay? But we call this a feature map because it maintains, as we wanted, this 2D structure. And I want us to consider two intuitions about the meaning of this creature here. So one thing I want to examine is what if we just take this one channel out of this feature map. Let's examine just this. And for example, it could be, let's say this is deep somewhere in the network. This channel would look like something like a map, especially if you use ReLU activations, then it's the most apparent because the ReLUs, they kill a lot of values. You're going to see a lot of zeros, a lot of black. You with me? And then this map is going to be about where there are things that this particular channel likes. Okay? Think about this. There is a neuron. It's a function of the receptive field. And it's a complex function. I don't know, it does many things along the way, non-linear, whatever. There are many layers. It's not just one layer on this, okay? It does something, and then it all comes down to a value that can be 0 in many cases, like the ReLU may kill it, or it can be some number. And what you will see is that this value indicates to what extent in that location, in this receptive field, I recognize something that I like, that this channel like. And every channel is going to be about something else. Some channels are going to be about things we don't really understand, we don't really get what the point there. And in many cases, you will see channels that do have semantic meanings that you can name. So in this example, this is a made-up example, but these things exist. This could be the channel that likes faces. So it fires up, this is like a neuroscientific terminology, it fires up when it sees faces. So when it's exactly on the face, the pixel is exactly the center of the face. So it's all white, and when it's, you know, overlapping but not all the way, it's kind of grayish. And this is what you're going to see usually. Usually, when you look into layer values, you're going to see mostly zeros, because think about all the things you can recognize at some intermediate level. For some input, most of them don't exist. For example, if this is a recognition network trained on ImageNet, you'll know these things later. And there are, I don't know, dogs, cars, whatever things. And then you see this one image. Most of these things, they don't exist there. So many channels can be even completely black. And when they're not, they might look something like this, like all black. And there is this thing we call a feature map. Okay, so each channel likes something, and it maps where are those things that it likes. Is this intuition clear? Yeah.
The feature map is the output.
It's not the output of the whole network. It's some intermediate, in some layer in the network. Okay, you apply convolution and again.
But this C is the number of channels in the input?
In the no. The input to the network is an image. So most likely we'll have 3 input channels, RGB. And then you'll have many layers. And say this can be, I don't know, layer number 22. And I look at the output. I call this the feature map that I got from layer 22. and this is what I see. And naturally, if this was only one convolutional layer, the receptive field is smaller and the semantic meanings are simpler, so you're not going to see faces. You'll probably see that it likes vertical lines and horizontal lines. These are going to be these filters. You have a list of functions that recognize things. The deeper you go in the network, these are going to tend to be bigger in size, like bigger receptive field, and more complex perceptually. Okay, we start with lines, goes to faces, then I don't know, keep on going and we'll recognize whether or not there is violent activity in a video. Okay, yeah.
Do H and W necessarily need to be consistent through the whole,
Consistent with what?
through the whole layer?
No,
Deep layer?
you can do whatever you want. I mean, think about classification, usually, okay, we'll see examples. Yeah.
I didn't understand. We have many features. How do you know, like, what is the input that we are testing like you say we are searching for faces, but we don't know what to search in order to classify.
Yeah, you don't know. You just, it's kind of a.
You feed it a lot of inputs and see what it reacts to.
No, sorry if it wasn't clear. This is a trained network. I already trained it.
Yes, but
And now I'm at inference phase. I'm taking this one image. I input it to the network. This one image.
Yeah.
This goes through the layers. There,
Yeah.
so all the neurons, they are applied. I get values through all of it. This is just the forward propagation.
Yes.
And say in some layer, I don't know, layer 18, I get this output from the layer. This is about to go into the next layer, okay? And I test it. I check what do I see there. And typically the things that I'm going to see are like this. So it's going to be a tensor, CHW, and if it's a batch, there's going to be the end of the batch, even if it's one, so it's going to be side one, okay? And I visualize. So I say, okay, why don't I show an image which is channel number something, instance number something in the batch, and then I only have H and W. Look at it as if it's an image. And then you see something typically looks like this.
I understood that part, but let's say if you're searching for faces and
It's not, you're not searching.
Yeah,
What I'm
but
saying
no,
is
no.
analysis. It's not like,
yeah, I got it.
Yeah.
But let's say that this layer, this channel recognize faces, but you input image with no faces.
okay.
So you won't see any.
So
this one will
it
be
can be
that.
all black.
Yeah, but you don't know which features you're looking for in advance. You say this,
Right.
This might recognize edges.
Yeah, but this is not like the output of the network.
Yes,
This is something that happens intermediately.
yes.
So I assume, so the reason you're asking is, how can I use this? Well, I'm not. The one who's using it is the next layer. And the next layer knows. It's trained so that if this has faces, it can sort of say, I can use these faces if I want to recognize humans, or I can use other things. But this is just like an analysis thing. You look at, and you also see, this is kind of a very ideal thing. So some channel can, like, you see it at some point in the course, like when we do visualizing and understanding. So a channel can like the noses of dogs and car wheels. I don't know. And some channels that do like things that either we don't understand, or we do understand, but we can't name them. Some kind of a visual feature that I can't name, and I see when it appears. But it's just an analysis. You go through it and you see interesting things sometimes. All right. Yeah.
Question. To make them recognize different things, you have to. Is it like a theorem that if you have the same architecture for all channels, then you'll get the same features to be recognized?
No, you do have sort of the same, I mean, the architecture is sort of symmetric, but what's different between them is the initialization. So before training and after training, what's different is the weights values. So each one of them is a function that can be written in the same structure of its receptive field, right? Only with different values to those weights. So this is why this channel, each value here is a different function of its receptive field than each value here. Okay, makes sense? All right, so this is one intuition. Let's look now at a different cut. instead of taking this one channel out of the feature map, what now I want to see is what happens if I take all the channels, but only in one spatial position. So, according to the spatial position that I chose, they all have the same receptive field. So, all these neurons here, all these values, they look at the same receptive field. And then I look at this vector that I have now, and it has some values. And this is sort of a coded way, which I don't know how to decode, but the next layer does. So this is kind of a coded way to say what I'm seeing here. So it's not just this one feature, one characteristic that I was looking, where there are faces, where do I see legs, where do I see eyes, whatever. It's the full description of what's in this position in the image in some sort of a coded way. Okay? So if I say, if I want to do some kind of matching between images, for example, or between patches of images, one thing I can do is sort of, let's take patches from many images, let's feed images through a trained network that does, I don't know, classification, take some layer, some feature map, and then take this bunch of vectors for different images, different patches, and see who are the nearest neighbors. This will help me, for example, if I don't know, if I have a picture of an elephant, and I can do this retrieval saying, oh, I have an elephant's head here, and I have an elephant's head in another picture, and even though the pixels color-wise and lighting, everything, they're very, very different, I could do this semantic matching between things, okay? So these are the two intuitions, like healthy intuitions about feature maps, okay? The receptive field coded in those positional vectors through all the features, and the feature maps that say, where is this thing that this channel likes? Let's get familiarized with another operation. This is called a transposed convolution. And the direction here is, we know about roughly how to keep the same size when we apply convolution. We even know how to decrease the size. However, we don't know how to increase. What if we want to we have an input and we want the output to be bigger, okay? So this is where we're aiming, and for this we will learn about a transposed convolution. So I'll just present the rule and then we'll analyze what's happening here. So in transposed convolution, we sort of do the other way around. So before we looked at the output and we said, let's take just 3 weights to multiply the input. Now I'm looking at an input value, and it sort of sends its value 3 times. I mean, when the kernel size is 3. So k times, chuck, 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 like this. And each value here is the weight multiplied by the same thing. And as I keep doing it, the rule is going to be that when there is an overlap, I sum it. So right now, x1 is going to be the sum of a multiplied by x2 plus b multiplied by x1. Okay? And as I keep doing it, I get all of these. And I don't want to waste time asking you about this, but look at what we're getting here. Okay, so think about it. Okay, let's look at the second row because it's full. So we have x1, and we got c multiplied by x0, b multiplied by x1, l multiplied by x2, and nothing. So what did I get here? What did I end up with? No, what do you call a layer that can be described by such a matrix? A convolution layer, right? So why am I doing all of this? Okay, why am I doing it? We ended up with a convolution. Okay, it doesn't matter. So it's flipped, right? Before we had A, B, C, but what does it matter when you're going to train something? So C is going to be what A was. Okay, it makes no difference. But here's where it comes in handy. When I do strided transposed convolution, I do the stride. You can sort of say that I do the stride over the output. So basically now, this is how it's going to look like. And now, when I do this, I can get an output that has a size that has more values than the input. Okay? And now think about this matrix. So what happens here is everything is the same as before. Only we killed some of the inputs that we multiply by them. If we kill some of the inputs, it just means kill some of these columns in the matrix, right? Everybody's with me? Are we good? So I kill them. And now we can recall how the strided convolution looks like not the transposed one. And this is where the transposed convolution name comes from. Okay? You see, when you have the stride, this is the transpose of this matrix. You may bump into the name deconvolution. Some people call transposed convolution deconvolution. It's a bad name because deconvolution in signal processing is a whole other thing. Okay? But you may bump into this term. All right. How are we with time? Okay. Now we're going to get a bit technical, okay? And we're going to talk about the implementation of a conv and the backpropagation to it. All right? Any questions so far? Are we good? Okay. So we need to think about how can one implement a convolution? And this is going to be something that you're actually going to do by yourself in the notorious homework 3. Okay? So one thing I'm sure about is that you're going to know this. The only question is how painful it's going to be when you do the homework. So let's try to look at it together. One thing I want us to recognize as a motivation here is that whenever we have this filter multiplies all the values that it sees, a good way to look at it is say something like, okay, I take all the values like this. So we had 3 by 3 by 3 thing, remember? I take all of them, and I flatten them to get this vector size 27. Then I do the same to the filter. And then I do a dot product between the filter and all these values from this window that it was seeing that I flattened. I do a dot product and I get one value out of it. Are we good? Which is the same as we said, right? Because you multiply a weight by everything, you sum it all up. This is exactly a dot product. Okay? Are we good? The thing is that we do this, it's not one dot product to the entire input. The thing is that we need to do this dot product separately with each window. So the strategy here is going to be, we're going to split it, all these windows, we're going to split them, then we're going to flatten all of them. Then when we want to do this dot product with the filter, we'll trick it as this matrix multiplication. Okay? So I'm just giving like the motivation, and now let's see how we do this. So this is the input, and these are our filters. All right? Now we're going to use this operation called unfold. Okay, this is how it's called in PyTorch. Okay, and what unfold does is exactly what I said. It's just taking those patches that can overlap, okay, and takes them out of the image, out of the tensor, and flattens them. So when I have n, cin, hw, and I apply unfold with providing the kernel size and the stride, it simply means every window that looks like this is going to become this vector. But I'm going to have many of these windows, so I'm going to have this list of flattened patches. Is this okay? Are we good? Okay. And so look at this. You see that in this example there is 2 by 2 by 2 here, right? In this particular window, this is sort of in the picture. It's kernel size of 2 by 2. So 2 by 2 by 2 is 8. I'm going to take all of these 8, and just flatten them to a long 8 long vector. How many of these am I going to have? Many. Okay, because these are overlapping patches, so it depends on padding, whatever. Roughly, if I use stride 1, so it's and the image is big, it's roughly the number of pixels in the image, but not exactly because the boundary thing. So if I pad it with, so if I have a 3x3 filter and I pad it with 1 in each direction, then I'm going to have the same, the number, then the length of this list is going to be the number of the pixels in the image.
So is it important to flatten in the one direction every patch, like to flatten in the specific direction, right? You can take it out different.
Yeah, you just have to be consistent. And when you do unfold, there is like, you can read in the, for example, Python documentation, there is like what we call row major. So you do the row, I mean, you go along the orders of the tensor. Okay. To make sure we understand, let's look at the size of the new tensor we have here. So it's an order 2 tensor, it's a matrix. And this thing is going to be n by sort of h, sort of w. Okay, depends on the stride, the padding, whatever. Okay. But roughly, if I do like this ideal arrangement, so it's n by h by w, which means, so n is the batch. Okay, we don't care about it over there. Okay. But h by w, so it's not by w, it's h times w, okay? H times w is because we have this vector for every position here. They overlap, so it's roughly, it can be like f for every. And then for each one, the second dimension is what we just flattened. C by h by lowercase h, lowercase w. Okay, so this is just an order 2 tensor, which is something that is easier for us to work with. So far, so good? Just this reshaping. We're okay? I'm concerned.
It's reshaped, but with values will be repeated.
Yes. This is why it's not really reshape, it's unfold. Okay, and anyone troubled here? Because I see low motivation. No. Okay. I'll be here after class if you still have technical questions about these things. All right, but not inside, but outside maybe. Okay. Then I'm going to reshape the filter, as I mentioned. So just as I flatten these, I'll flatten the filter tensor. So now it's going to be C in HW by C out, which is this number of filters. So each filter separately becomes a vector. Okay, so the green thing here becomes a vector.
You flatten it the opposite way for matrix multiplication, or
The what? Sorry?
you flattened it the other way around for matrix multiplication?
What is the other way around? What is the right way?
In HW is in the opposite.
Why it's not C out first?
Yes.
So you can see that I'm about to do matrix
okay.
multiplication here. Okay. So now I can take this matrix and multiply by this matrix. Okay. And just think about the dimensions here. Okay. What I'm going to get. So the healthiest thing, I'm not going to educate you about matrix multiplication, but the one tip that I can give is that whenever I do any tensor multiplication, matrix multiplication, whatever, always think about a matrix as a vector of vectors. It's the best way to think about it. So this is, you can think about this as this vector of row vectors, and this as a vector of column vectors. So for each value, for each output value, I'm taking the dot product between some row here and some column here. So a column here is the value of the filter, and a row here is all the values in a window. And when I sum them up, it's exactly what I want. This is the motivation. But also just think about the dimensions of these matrices. So NHW, and then we have this. This is the same, so it's a valid matrix multiplication. C in HW, C in HW. This collapses, boom, and I get NHW. I get this thing which NHW, C out. Okay, this is one value per each C out and each window from these overlapping windows, I get here one value. Okay? So what do I have so far? Unfold to the input, reshape to the filter, multiply them, okay, matrix multiplication, to get this creature. And what I do now is what we call fold. Fold means taking these flattened vectors and rearrange them, but this is a very simple fold. This fold is actually equivalent to reshape, okay? But it's healthier to use fold after unfold, but it's just reshaping them, okay? With 1 by 1 stride equals 1. It's just taking them and reorder them like to be these in this 2D structure, okay? Because this is where they came from, okay? We flattened them, we did all the actions, now we're bringing them back, okay? You'll have this recorded and you have the slides, and then you'll do this in homework 3. So you'll go through this and you'll implement it by yourselves and see. Okay. One comment about what happens when we want to do transposed convolution and not convolution. Okay. So what you do is you just switch the sizes. So now you do unfold with 1 by 1, and you do the fold with the kernel size and the stride. So think about it when you do transposed convolution. So here is just simply like a reshape, because remember in transposed convolution you take every value and you like spread it, but you're only looking at one value. So you're taking this one value, then you do the fold, and the one important thing you need to know about fold that is also different from just reshape is that it sums overlaps. So when you do fold, you sort of do this transposed convolution-y thing that you saw. You take the value, you spread, then you take the next one, you spread, and whenever they overlap, it subs. So you get this. The next step, I'm going to be centered here, and I'll have overlapping values, and then they sum up. And this is what gives you transposed convolution. Okay? Now, let's in general try to think together just the direction, not like the exact thing we're going to do in a second, okay? But the direction of how would you think about doing back propagation. So we understand convolution, we understand why it's good, we understand how to do it, we sort of understand how to implement it, the forward process, okay? Now, how do you backprop? Any ideas? Think about some observations that we had. Like for example, is a convolutional layer a special case of something?
Some perception.
Sorry?
You need to average over the perception area.
Yeah, I'm looking for like some very
Linear,
simple.
there is a specific linear.
So it's a simple case of linear. So one good thing is we know how to backprop linear layers, right? Convolution is a special case of a linear layer. So one good thing is it's possible. Now we can just think about the rules we had for backpropagating through linear layers, okay? And just apply them to convolution. So let's think just about this linear part. So we had in the last class we were talking about backpropagating through like this vanilla layer that was linear and then some kind of non-linear activation. Let's throw away the non-linear activation. When you only have the linear, okay, and you do backpropagation, and say I already have the gradient with respect to some layer, now I want to go one layer to the back. It's actually very simple. Remember, it was this elegant thing. I just multiplied by the weight matrix. But when I did the forward pass, I always multiplied in the weight matrix transposed. And you remember we had this list of 4 differences between the back propagation and the forward propagation in vanilla layers. So for example, it was linear and it didn't have bias. And one thing was you don't do the transpose. So whatever the matrix, think about it, a linear layer you multiply by some matrix. When you do backpropagation, to a linear layer, it's like applying a forward layer, but with the transpose of this matrix. So far, so good. Now, we know how the matrix of a convolution looks like, right? And then when we go back, we need to take the transpose of this matrix, which is what?
The same.
No, it's a transposed convolution. It's a conv transpose, okay? So if you do just 1D, it's just so the back process, it all comes out from the linear layer, okay? Because when you do the back prop, you use the transposed matrix, and the transposed matrix of a convolution matrix is transposed convolution. Doesn't matter if it has tries or doesn't have tries or whatever. Are we good? Is it okay for now? When we go to 2D, things get messier, but still quite elegant. So a healthy way of thinking about a 2D convolution, or convolution in general, is sort of like having this vanilla neural network that travels around the image. Because when it sees only this one receptive field, okay, or this one layer C1 receptive field, it's like a linear layer, but only for this receptive field, right? Are you with me? And then it's kind of like this batch of patches. Then I do the exact same operation in a different location. Okay? So for this specific receptive field, the place where I get a matrix, which is sort of the input-output relation as in the vanilla network, is the C in, C out. Okay, because for this window that I'm looking at, I have this bunch of C in, and I have this output, which is C out, sort of, because the C, it has a window side, whatever, it's C in lowercase h, lowercase w, going to C out, right? Are we good at this point? So I roughly do the same thing, and I need to transpose the C out with the C in lowercase h, lowercase w. But for the special dimensions, I need to do, I need to sort of maintain the same locations. Okay, so.
You see the special dimensions?
Yes.
What are those referring to?
Sorry?
What are those referring to?
Like spatial.
The spatial.
Yeah, like merchavi.
Yeah.
Okay. So let's look at. So it's kind of it's going to be messy, a bit messy to follow now. I'll do it slowly, and then you have the slides and everything, and then go through it again. And then when you do it in your homework, and you look at this, and eventually you'll understand it very well, I'm sure. Okay, but try to be with me now. Let's go for the backward operation. And first, let's define some names for things. So you see there is X, Y, and K. X is the input, Y is the output, and K is the filter. But after all of them have been reshaped, okay? This is like the notation here. X is after the unfold, Y is before the fold, and K is the reshaped kernel. So they are all matrices, order 2 tensors. Good by now, okay? All right, now, what do we want? We're getting this is a layer in some network. We're back propagating now. We get the gradient with respect to Y, okay? And we need to calculate, remember from the ending of the last lesson that we had, you want to calculate the gradient with respect to two things, the input and the parameters, like the values in the kernel itself. Okay, motivation is clear? So, this is the direction we're going now. We're doing back propagation. We get the gradient of Y, we want to get to the gradient of X and to the gradient of K. So the first thing we need to do is, instead of fold, we do unfold now. Okay, just the direction, you know, I had this, I'm going to this. Before this was fold because I was going from this to this. unfold one by one. So it's just reshaping. I have this list of vectors. For each pixel, there is a vector on the side of the channels. Okay? And these are of course the gradients. And I reshape it. Now, I change the order now. And you remember when I go backward, say for vanilla network, I multiply by the weight matrix. This is the weight matrix. I'm going to multiply it, but remember what do I have to do? Transpose. Otherwise it's not valid, right? Look at this matrix multiplication. I cannot multiply this with this because see how it is here and can do it. So I transpose. Now it's valid. Okay? I can multiply this by this, and the output size is going to be, look at this dimension. So here it's NHW C out, and here it's C out, and then C in HW. So the output is going to be NHW C in lower H, lower W. Okay, I know many dimensions, okay, but just look at its value. Okay, so I take Y grad multiplied by K transpose, and this is what I get. I get that the gradient of X is Y grad K transpose, and don't remember this is before the folding. So when you go from this X to the tensor shape, now I need to fold. Okay? But there is one more thing that we need, which is the gradient with respect to the kernel. So this is also very similar to what we had in vanilla neural networks. So think about it. I know that Y is the result of K multiplying X. So if I'm asking what is the derivative of K, of Y with respect to K, so this derivative is going to be X, speaking like roughly simply, right? Y equals xk. So the derivative of Y with respect to K is X. So I have to be careful about all these transposes and stuff like this. But the gradient of K is Y grad transposed. Okay, look at this. I transpose, then I get C out NHW, which is valid because I have here NHW, and then I get C out C in lower H, lower W. I reshape. It's a simple reshape. It's just saying that instead of C in HW, it's C in HW. Okay, so I get this, and then I simply reshape to get this tensor. Okay, I know it was like hectic now. It's hard to through the class go through all the thing, but you sort of got the process, and you can go through it again, and you'll implement it, and you'll see this technical thing, and it's nice. It's important. Okay, there are many people walking out there who don't understand really why backpropagation works through CNNs and how to implement it, and then it prevents them from really deeply understanding how to do bigger, meaningful actions. All right. Okay, the hard part is over. Lighten up. Okay, we're good. Now it's all easy to you. Okay. Here's another operation that people use in CNNs. Super simple. Okay. This is called max pooling, and this operation, what it does, it's also inspired from neuroscience in some way, but it does something that is very simple. You have this window. Usually, you like the windows not overlapping, so it's like a grid, and at each time you just pick the highest value and you only take it. So it's another way, instead of like strided convolution, it's another way of getting a smaller size tensor. Sorry? Okay, so you get a smaller size tensor. Okay, and the motivation here is the idea is that remember the feature maps that like and don't like things? If there is something you like, take it. It's going to have a higher value. So you kind of get the gist of things. So if you have this big window and there was this one face there, I'm going to take just this value, okay, and go on. So it's another way. It's design choice that you can make to get to reduce the resolution inside the network, and people use it a lot, and it doesn't require any parameters. You see, there's nothing is learned in this layer. Usually the stride will be the exact window size, so it will be non-overlapping, but not always. Sometimes people do things that do overlap. Oh, and it happens for each channel separately. Okay, so for this channel, this value is the biggest. I take this one. For the channel behind it, it can be this other position, and now they're going to be one behind another here. So it's kind of a way of lowering the resolution, so that for every channel I take the important things, and they're going to be together in here. Okay. And finally, here is an example of what a convnet would usually look like. So this is for classification. Okay, and this is VGG. So from Karen Simonian and Andrew Zisserman from almost a decade ago. Shit. Okay, and so this is called VGG, the Vision Geometry Group in Oxford. This is why it's called this way. And this is like a classical way of how a very simple CNN would look like for classification. So what do we have here? So convolution plus ReLU is all the blue things that you see. And then you see we have max pooling layers. And what you see usually is happening, you start with the size of the image. Back then, people used to process, I don't know, size 224 by 224. So the scale of the image is to this size. And the first convolution brings you to 64 channels here. Then you do a few convolutions in this resolution. You max pool, you get lower resolution. And usually what you see is that the deeper you go in classification, resolution decreases, channels increase. Okay, it's like saying, I don't need to know exactly what's in every pixel. The deeper I go in the network, when I want to semantically understand what I'm seeing, I want to have more, say, words to describe. Remember the intuition about the receptive field vector? So I want to have bigger vector to describe more complicated things, but I want it to be spatially less wide, okay, narrower spatially, because I end up in nothing that is special. I want to say this is an image of a dog. Okay, so the more I go, resolution would decrease, but the number of channels increases. And then at some point, so close to the end of the network, this is how you can tie this with the things that you already know about vanilla neural networks, things you've been doing. You'll get to the resolution sized one by one, the resolution, and then you go into fully connected layers. It can be one or more layers, and then you go to what you're already familiar with, like softmax, and you do the classification. There are other ways. So at some point, people stopped doing these fully connected things, and they did this thing called average pooling, which is sort of average. So you get the resolution becomes really small, like 4 by 4, and then you just average spatially everything, and you don't need it because if you count the number of parameters in the network, in those fully connected layers, there's like 10 times more parameters than the entire this part of the network. Okay, so this is like the classical thing. This is what we do. You'll learn about more architectures next week and ResNet and whatever. But this is like the basic thing.
This is for classifying the full image, right?
Yep.
Not for like detecting small things.
Yeah, it's not object detection or things like this. This is classification. Okay, we're close to the end. Just want to mention so that you'll be like familiarized with some other types of convolutions that exist. For example, one thing we have is depth-wise convolution. Okay, I was asked about this first at some point today. So depth-wise convolution simply means that I kind of do the convolution not only on the spatial dimensions but also on the channels. So I kind of also the filter you can imagine travel also into those channels. This is a thing that exists. Sometimes you have a reason to do this. Okay. Another thing, and this is like this was already presented in the first modern CNN paper, the AlexNet, in 2012, is called group convolution. This is mainly to save on parameters. So instead of the filter, you remember the C-in thing? Instead of the filter seeing all the input channels, it kind of, you have different filters that only see groups of the input layer. So if the output size is 6 and the input size, 6 channels and the input size is 12 channels, so you can save on parameters by saying that, sorry, this yellow filter here, it's only seeing this group. So I kind of, it's the same thing as if you like chop it in the channel dimension, and then you apply a different layer to each group of channels separately, and then you concatenate again. Okay.
How much do you save on parameters there? It's like
Oh, a lot, because think about it. You see these 4 lines? These 4 lines could have been 12 lines. And this goes to this and to this and to everyone in the group. Okay, so we can think about it, how much you save if you divide it. Okay, and one other thing from, so this is called dilated convolution. Dilated convolution simply means having those holes. So you can have the filter bigger, but not continuous over these. And there are reasons to do that. So the original paper had some ideas about aliasing and things like this, like signal processing motivation. Not getting into it, but it's sort of like a motivation, and this is another parameter. So when you define a convolution layer, say in PyTorch, the things you specify, they're like defaults, but the things you specify is the kernel, so the h, like lowercase h and lowercase w, like the special sizes of the kernel, the numbers of out channels, the numbers of in channels, or even though you kind of have, you provide it, but it must match the previous layer. Okay. So all the dimensions of the filter, these are 4, but then you also say padding, what the padding is going to look like, and the stride, and the dilation. So the default is dilation 1, which is practically no dilation, and the stride is 1, which practically means no stride, okay, etc. But just know that these exist, okay? That's it. So next week, you're going to have Shai talking about practical training things. So, whoops. So, what we were doing in these past 3 lectures, we kind of got the structure, the theory, everything, and I presented a picture as if everything is like very solid. But in real life, this science is much more empirical science than a theoretical science. And so talking about these ideal things in neural network is one thing, but then if you really want to get things to engineerically work for you, you'll have to use this bunch of tricks in your network. So you'll need to consider how you initialize the weights and use augmentation for your data and all types of regularization for the training procedure, and know about the thing called dropout layer and batch normalization and hyperparameter tuning and other things like this. So this is like the real practice. And so you're going to do this on Monday with Shai, and then in the tutorial of that week, you will have Raphael explaining to you about CNN architecture. So we saw this basic idea. So it will take you to a trip through time, a journey through time from the first architectures and gradually understanding the architectures that we're using today. Okay? We good? All right. Thank you for listening. So the next couple of classes are not going to be with me, but I will come again for generative models class. So thank you everyone and see you at some point. I'll be around here if you have questions. Thank you.